Hello, good day everyone. Today's topic is ensemble learning, bagging and boosting information. So what is the ensemble learning? Ensemble learning combines multiple machine learning models to create a stronger and more accurate and robust models, primarily using bagging, uses variances or overfitting, or boosting reduces biases and improves accuracy. Bagging, like random forest, trains models in parallel on random subsets, while boosting, like XGboost, trains models sequentially, with each correcting the errors of the previous one. So, Ensemble learning aims to improve machine learning predictions by combining the outputs of multiple base models, weak learners to form a stronger learner. And bagging, boosting, bootstrap aggregate. Bagging reduces model variances and helps prevent overfitting by training multiple independent models in, in parallel. Methodology uses bootstrapping, which involves creating multiple training subsets from the original data, sampling with replacements. Training base models are trained independently and in parallel. Aggregation predictions are combined using voting, classification, or averaging regression. An example, random forest trains multiple decision trees on random data subsets. Best for high variance, complex models, example, deep decision trees. And next is boosting. In boosting aims to reduce bias and improves accuracy by training models sequentially. Methodology, each new model focuses on the errors, misclassified data points of the previous models. Training models are built one after another and samples are weighted based on difficulty. Aggregation, weighted voting, or averaging is used to combine models into a stronger learner. Examples, gradient boosting machines, GBM or XGboost, adaboost, best for weaker learners. Example, shallow decision tree. Key differences, bagging versus boosting. So normally, bagging, bootstrap, that is aggregating, or boosting. Goal is to reduce variance in overfitting and bagging and reduce bias in underfitting in boosting. Training parallel independent, but in boosting sequential dependent. Data usages or in bagging random subsets bootstrapping and boosting it's weighted subsets focusing on errors. Model types strong model complex and boosting weak models very simple one. And final decision like voting or averaging into bagging and in boosting weighted average and examples of the bagging or random forest and boosting or medium boosting. When to use bagging when facing overfitting high variances, when to use boosting when facing underfitting or high bias or seeking high accuracy. And ensemble learning, like what is ensemble learning? Ensemble learning is a method. Now we will see in depth about the ensemble learning. Ensemble learning is a method where multiple models are combined instead of using just one. Even if the individual models are weak, combining their results gives more accurate and reliable predictions. Multiple models uses many small models together. Better accuracies or like combined results improve performances and reduced errors or mistakes of one model are balanced by those of others. And simple idea like taking advice from a group instead of one person and this is how the ensemble learning works. You can see in the representation training data, and it is bootstrapped samples and base learners like learner 1, learner 2, learner 3, and individual predictions yes, 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 no, and it will be combined in the ensemble predictions, and you will get S. And ensemble learning can be divided into bagging, boosting, and stacking. And in boosting base models, you can see uh, this is how the predictions are done. And from the predictions, again, you do base model and prediction. The training is modified based on the predictions. And again, you to be trained, and the model will predict, and you will get the final outcome. So it is a repetitive process until you find the optimum predictions. The predicted value is optimum. And next is bagging, different subset of training data are used for base model training, and most frequent or average predictions are done, and you obtain the prediction finally, or you reach the prediction. And stacking, where different models are used for different data sets, and meta learners are obtained, and from there you do the predictions. And types of ensemble learning, like we saw already, there are three main types of ensemble methods. Bagging, bootstrap aggregating. Models are trained independently on different random subsets of training data. Their results are then combined, usually by averaging for regression or voting for classification. This helps reduce variances and prevents overfitting. Boosting, models are trained one after another. Each new model focuses on fixing the errors made by the previous ones. The final predictions is a weighted combination of all models, which helps reduce bias and improve accuracy. Stacking or stacked generalization. Multiple different models, often of different types, are trained, and their predictions are used as inputs to a final model called a meta model. The meta model learns how to best combine the predictions of the base models, aiming for better performance than any individual model. While stacking is also a method, but bagging and boosting method is widely used, and let's see more about them. And bagging algorithm, a bagging classifier can be used for both regression and classification tasks. Here is an overview of bagging classifier algorithm. Bootstrap sampling. The dataset is divided into multiple subsets by sampling with replacement, creating diverse training data. Base model training, a separate model is trained on each subset independently, often in parallel for efficiency. And prediction aggregations, predictions from all models are combined using majority voting, classification, or averaging or regression, OOB evaluation. It is nothing but samples not included in a subset or used to evaluate model performance without crossing validation. Finding predictions, the combined output of all models gives a more reliable and accurate results. Implementation, like we'll be importing libraries and loading data, and this is sample code here, and loading and splitting the iris data sets. And next we are creating the base classifiers from this classifier class, and creating and training the bagging classifiers. After that, we are making the predictions and evaluating the accuracy. The output is what the accuracy value we have quoted here as 1.0. Boosting algorithm is an ensemble technique where multiple weak models are trained one after another, and each new model focuses on correcting the errors of the previous one to build a strong models like we saw in the picture earlier. The process works as follows. Initialize weights start with equal weights of all training data, training weak learners, train a simple model on the data set, sequential learning. Each new model learns from previous errors, weight adjustments, misclassified samples get higher weights, so future models focus more on them. Implementation, like you can see, there is a model we import libraries and modules, adaboost classifiers are imported, ensemble, and loading and splitting the data sets here we go. And next is the defining the weak learners, and after that creating and training the adaboost classifiers, and after that making predictions and calculating the accuracy. So here again the accuracy is 1.0. Benefits of ensemble learning in machine learning. Ensemble learning is a versatile approach that can be applied to the machine learning model for reduction in overfitting. By aggregating predictions of multiple models, principles can reduce overfitting that individual complex models may exhibit. Improved generalization, it generalizes better too unseen data by minimizing variances and biases. Increase accuracy, combining multiple models gives higher predictive accuracy. Robustness to noise, it mitigates the effort of noisy or incorrect data points by averaging out predictions from diverse models. Flexibility, it can work with diverse models, including Bayesian trees, neural networks, and support vector machines, making them highly adaptable. Bias variance trade-off techniques like bagging reduce variance, while boosting reduces bias, leading to better overall performance. Ensemble learning techniques like random forest bagging, categories bagging, and random forest constructs multiple Bayesian trees on bootstrap subsets of the data and aggregates their predictions for final outputs, reducing overfitting and variance. Random subspace method, it's under category value. And here, training models on random subsets of input features to enhance diversity and improve generalization while reducing the overfitting. Gradient boosting machines, GBM, under the category boosting. Gradient boosting machines sequentially builds mutation trees, which each tree correcting each errors of the previous ones, enhancing predictive accuracy, iterate. And extreme gradient boosting, XGboost, under the boosting category, XGboost to do optimization like tree pruning, regularization, and parallel processing for robust and efficient predictive models. Adaboost, adaptive boosting, under the category boosting, adaboost focuses on challenging examples by assigning weights to the data points, and also it combines weak classifiers with the weighted voting for final predictions. And cat boost, under the boost category, and cat boost specialization handling categorical features natively without extensive probability processing with high predictive accuracy and automatic fitting handling. So here we see the bagging versus boosting in machine. Little bit elaborated. We have already seen both the differences. We'll see elaborate. Bagging and boosting are both ensemble, learning techniques used to improve model performance by combining multiple models. The main difference is that bagging is the variances by training models independently. Boosting reduces biases by training models sequentially, focusing on previous errors. So here, this tutorial presentation will explain about the bagging. So we have the classifiers, principal classifiers, and original data, and bootstrapping, and aggregating. These are the steps happens in the bagging. And next, you can see the boosting. Original data is subject to the classifier, principal classifier, and again, you segregate the data, and the output is the omitted data is given to the weighted data, and it is set to the another classifier, that is execute classifier. Again, the unclassified ones are given into the weighted data. It keeps on going and fixing the errors and classify the data until it reaches the optimum level by reducing the errors in the given data. Understanding bagging. Bagging bootstrap application aims to reduce model variances by training multiple models on different random subsets of the data. These subsets are created using bootstrapping, where data points are sampled with seed placement. Each model is trained independently, and their predictions are combined using voting or classification of averaging or for regression. As models are trained independently, bagging works well with high variance models like ratio tree uses random sampling with replacement training. These models independently combines predictions using voting or averaging, reduces overfitting using random forest predict risk predictions and medical diagnosis systems. Under understanding boosting, boosting focuses on improving model accuracy by training model sequentially. Each new model pays more attention to the data points that were misclassified by previous models. Over time, the ensemble becomes better at handling difficult cases. Boosting is effective for reducing bias and works well even with weaker learners. Trains models sequentially, gives more weight to misclassified samples, combines models using weighted voting, reduces bias used in fraud detections. Differences between bagging and boosting. Here we go. Now let's see a tabular differences between bagging and boosting. Features, bagging and boosting. So what features here we are going to discuss is training size type, trains independent models, and boosting trains sequential models. And main goal of these variants are here boosting reduce bias and handling errors. All samples treated equally in bagging. Focus on misclassified samples in boosting. Overfitting, it is a less sensitive to overfitting in bagging, more prone to overfitting in boosting. And parallel training, yes, it is support parallel computing in bagging. No, it does not support parallel computing in boosting. Sensitivity to noise, it is not affected by noise and outliers by bagging. Sensitivity to noise and outliers, yes, it is there in the boosting. When to use which technique? Use bagging when the model is overfitting and has high variances, especially with patient tree. Use boosting when your model underfits and you want higher accuracy by learning complex patterns. That's it about the ensemble learning.